behind that, which is very sophisticated. I will not go into that, but just to give you a feel for it. Let's, okay. Here is the operating characteristics of the transistor. This is where the gate is. This is the gate oxide. And you have the arsenic diffuse regions on both sides. And here is your boron dope region. So you cannot pass any current. There is a PN junction, which has a higher resistance. So if you apply 0 volt at the drain and 0 volt at the gate, nothing happens here. There is no IV trace. As soon as you apply gate voltage, which is above the threshold voltage, that means voltage at which you have made inversion and you have formed a very thin skin here of negative charges, because once you apply positive charge, the positive charges get repelled down here and you create negative charges in the thin skin, and then N+2 regions start conducting and you have a device where you're starting to get some current. And this particular region starts pinching off, and then beyond that, if you apply voltage beyond VD sat, as it is called saturation voltage, you saturate on the current, and on this side, this IV curve flattens out. You cannot get any more current out of this. So it's like if you have a diode, let's say you have a light emitting diode, LED. Once you start applying voltage, it will start glowing a little bit bigger, and then it will glow to the highest illumination that you will not be able to glow it anymore. So that's the basically nut out of this. So this is NMOS, there is PMOS as well, works like that. Now, where do we go from there? I don't know why I'm not able to go forward. Okay. Here is the device characteristics that I'll be showing. The same device, when you plot the drain voltage versus the drain current, you get multiple curves depending upon what gate voltage you applied. Higher the gate voltage, higher is the current. So this works like a faucet in your kitchen. You have pressure of water coming in the line from one side to other side, which is like a current. And you modify that current with the drain voltage here, and also with the gate voltage. And higher the gate voltage, more the faucet is opened up, more current keeps on coming. So this is a very simple way of looking at it on the device. And here is a region where device has linear characteristic, and it's a triode region as a vacuum tubes, if you want to consider that from that old knowledge. And in the saturation region, your currents are flat. And amplifier works in the saturation region, which I'll show you in the next slide. So basically, this works as a switch. And here's the electrical diagram for that. For NFET, you have this voltage is more than threshold voltage. Then this current starts flowing, so this switch gets closed. So it's an on switch. And when the gate voltage is less than the threshold, you're not able to get any current. So this is an off condition. So you have on and off. And for PFET, it's exactly opposite. You become off when the drain voltage is greater than the threshold voltage. And on this side, when the gate voltage is less than threshold voltage, your device is on. So basically you work as a switch, and this is where the digital devices are fabricated using this principle. Oops, I'm going too fast for some reason. Okay, here is the transfer characteristics of the same device. If you plot VDD versus gate voltage, and here is the electrical circuit diagram where you have the gate voltage transistor and you have a power supply VDD, and the output comes out of this transistor, which is VDS, and that output is plotted on y-axis, and the input is your gate voltage. And here is a region where you're going through the saturation that I showed before. And you can get amplification. You can see it. If you operate at this point, for example, and if you apply a sinusoidal wave of this magnitude, output comes out with huge magnitude that is about maybe 3-4 times magnified. So that's your amplification. Now, how do you exactly make a transistor memory work? And here is a simple chart. So in cross section, electrically, this has a bit line and a word line, and I'll show you what it means. You basically have the transistor, which is built up here in the cross section, and this is called word line. And then the contact, the drain contact, has a bit line, which is the metal line. And this is bit line, and this is word line. And once you charge this transistor using word line and bit line, the capacitor gets charged. So all the current that comes from the transistor is stored into this as a capacitor. And when you want to write this cell, so that becomes 1 bit. And if you want to write this, you want to bleed this charge, and then you write 0. So what they do is this word line, this is an array of transistors. You apply word line, so voltage is turned on. And now you are going to read which transistors have state 1 and which transistors have 0. And basically, when bit line is turned on and you keep that voltage on, and it starts bleeding into these devices, especially if it is a 0, this capacitor will start getting charged. So this voltage goes down. So through a sense amplifier, you can detect that. Here, this doesn't change because this is already charged. So between this bit line and that bit line, there is a voltage difference, which is detected. So you can tell which is 0, which is 1, or which is turned on and off. And you can write the cell as well. So that hopefully gives you some feel for how these transistors are used as switches. You build Boolean logic, you build circuits out of it, and then you build memory arrays, which can be as big as 64 gigabyte. Now, we will talk about manufacturing process. So how do you manufacture these devices? So you start with a wafer, you oxidize it and put another dielectric layer. Then you use photolithography, where you're going to be printing images, and I'll show you how those machines look like and what their operation is. And then you etch it through to form permanent shapes into the oxide and nitride, and into which you form, you deposit films, and thereafter you make interconnections in the back end. Then you test the wafer, and then you dice them, and then you make package. Here are some cartoons which will give you a feel for how it is done. And I'm going to go through each of these processes separately on separate slides. Photoresist is a material which is sensitive to light. And you have a machine where you have a mask through which light is shined. And when the light comes down through the hole, you will be exposing this photoresist, and then you develop it out and you form a shape where now you have access to oxide, into which you reactive ion etch, and you dig into this oxide there further and make permanent images. Into that, you can put layers of films through atomic layer deposition process, which I'll explain to you how it is done. And this is how you basically make a transistor. And then afterwards, you put either aluminum in metal lines or copper. If it is aluminum, you deposit thick aluminum films and you etch it with reactive ion etch and fill it with oxide as a dielectric. So they are separated. If it is copper line, you start with the dielectric, you etch through, and then you electroplate copper. So some of these process details I'll be showing you in the next slide. For example, in photolithography, this is the machine. Now, this is the very smallest machine that you could see. The next one I'm going to show you is how big the real machines are. But this explains the principle. You prepare the wafer, you coat it with the resist, you pre-bake it, you align and expose it through these slots that are in the mask. And then you develop that photoresist like a photography film. And then you etch through these features with the resist as a mask. And on the machine here, which does the alignment and exposure, basically you have a source of light, which comes through a bunch of mirrors and optics into an XY stage where mask is is loaded. And through the mask, light comes out wherever there are holes, and it goes through a bunch of optical lenses to focus it onto your wafer. This wafer moves in an XY stage, and you die by die, you print them, and entire 300 millimeter diameter wafer is exposed in this fashion. Here is your cassette in which all the wafers are loaded. So this is automatic operation. Wafers just keep on going through the machine. Now, this will give you some feel for how that optics works. And this is through the EUV lithography system called UV lithography. This is extreme UV. That means you're going to the shorter wavelength of the UV spectrum. There is a carbon dioxide laser beam, which comes out and gets focused onto these mirrors, and then down from reticle, it goes down into your wafer stage. And then this wafer stage moves, and then you are exposing these chips. What this allows you to do is shrink your image sizes, and then you can get images down from 45 nanometer all the way up to, say, I can't see from here, but it goes all the way up to 10 nanometers. And it allows you to build higher and higher transistor densities. So at the end, you will see 100 million transistors per millimeter square in 2019. So to that scale, you can bring it. Here is the progression that we are having in terms of years, and it tells you the half pitch, or it tells you the minimum hole dimension. The smallest hole you can print is 18 nanometers, which goes down to 10 in 5 years. And that's the progression with which people are actually fabricating these devices. Excuse me. This is your NXE 3400 ASML UV machine. This is a very sophisticated machine made in Netherlands. It weighs 180 tons. This is the actual machine, lithography machine, state of the art, recently built, and it costs $140 million. And it does process 170 wafers per hour. So you need that kind of throughput to run thousands of wafers per day operation in a fabrication facility. This company is very high tech. This has 700 PhDs. It has 7,500 engineers, 23,000 total. And this is the only one that is making this lithography machine for the smallest resolution that you can possibly get. Nobody else can compete with this. They do not have the know-how. So we are at the mercy of this company to make silicon chips from here on. And the critical dimension that you can print is wavelength divided by numerical aperture of your optics. The current numerical aperture is 0.33, which allows you to get down to about maybe 10 nanometers. And then when you go to numerical aperture of 0.55 from 0.33, you can get the resolution of less than 8 nanometers. So that's the present capacity. Going beyond 8 is very tough. We'll see what the exact path looks like, but this is where it is. This is the state of the art. After lithography is done, this is reactive ion etching, where the same wafer goes into a vacuum chamber, which has a diode, a bottom electrode and a top electrode. Top electrode has plus voltage applied, bottom electrode has negative voltage. And fluorine, for example, is a species used with positive charges. And because of the voltage difference here, they get accelerated with very high velocity and impinge upon this resist with the mask that has opened up. And you can go through this and etch into this oxide shown by green color. If your line widths are large, you can get away without reactive ion etch. You can do a wet etch in dilute HF and then open up this image. But the undercuts are huge and you cannot make any fabrication devices beyond 30 nanometers because tolerances are just completely gone. So you need straight walls, and that is where reactive ion etch process comes in. This is key. This is repeated at every mask level. There are about 40, 50 masks that are used in the entire process. And different chemistries are used for different materials that are being etched, obviously. So this is the basis of it. Next, we will talk about film deposition. So once you have made a trough shape like that, so this will be, say, 10 nanometers wide and maybe another 10 nanometers deep. The first thing you want to do is you want to put a seed layer, for example. When you want to build a metal line, you need to put a seed layer onto which copper could be plated. And if you try to do this with conventional processes like sputtering, you do not get good coverage on the side walls. You only cover at the bottom and the top, the flat surface. So ALD is the key process that is used, which is what it is shown here. So basically they use precursors, chemicals that will make the materials that you want deposition of. So if you want, say, aluminum, you bring aluminum oxide, and it's the TMA is the chemical name, which you purge through. And then very small monolayer is formed, and then you purge again. Then you bring in another another squirt of that material, and slowly, layer by layer, you get it to the actual thickness that you want. So this is really surface chemistry, very advanced surface chemistry under vacuum with very specific chemicals that are extremely high purity. And you form these layers, and then you get very thin layers that you need on the top of the topography that you have created. So this is called atomic layer deposition, because you are basically depositing atoms by atoms. Now, once you have formed this seed layer by ALD, shown here by dark line, next is how do you put copper into this, because that's your copper line, right? So basically they go into an electrolysis bath where you have two electrodes. There is a copper source electrode. It's called anode, and the cathode is where your wafer sits. And this is in an aqueous solution of sulfuric acid and copper sulfate and water, DI water. Once you apply voltage, the copper that is dissolved accelerates towards the wafers and start depositing into these cavities that we have created, coated with ALD process of a seed material. Why do you need seed material? Because this gray color is oxide. It will not conduct. You need a conducting film onto which copper will start depositing. So that's why you need seed layer. Now, seeding, this is a good fill, but you always don't get it. Sometimes you get voids or sometimes you get seams. And these two types of structures you do not want, because they do not make good electrical connection. Your wires will break after a running chip for, say, maybe 10 hours or 15 hours. So smart chemists have found out solutions to this. So they add something called accelerators and something called suppressors, blue and red. Those are the colors. So what are accelerators? The accelerators are the chemicals that will adhere more onto this bottom line, and then it will give you a higher deposition rate or higher electroplating rate at the bottom of the groove versus on the sidewall, so that you come up and the top halfway. Now your aspect ratio is a lot less. Aspect ratio is the height versus the width of this line, H by W. So this is about 5. So when you make aspect ratio around 2.5, you add the suppressors so that they will be suppressed, and then you can continue filling this remaining cavity. Entire fabrication is done and electroplating is completed. You have overfill, and this copper needs to be polished, and they use chemical mechanical polishing wheels onto which wafers are put, and they are polished down so that excess copper is removed. Now, when all in good, all these processes are conducted, this is how the wafer chip looks like in cross section. This is at the bottom, you had silicon wafer, you build the transistor. Then you use tungsten to make contacts to the metallurgy above. And then you build copper 1, which is first metal, second metal, third metal, fourth metal, and fifth metal. So this is a chip with 5 levels of metal. Nowadays, they can go up to 8 levels of metal. So on the top of transistor, there's a huge metallurgy that is involved. And all these light color layers are basically dielectric films that are put on so that these lines are insulated from each other. So you do not have any crosstalk between the two. On the top, the contact is made using a lead-free solder bump, which is a huge size, like a rock it sits. And this chip is flipped so that when packaging board comes, this particular seed layer, the solder bump will make the contact, and then you can use it on your package. So that's the way the entire chip looks like. So silicon is a very small amount of this, and most of the processing material that goes on is coming from your metallurgy. So let me give you a feel for what advanced packaging layout would be. You could have multiple chips put on on a board. You can have a package substrate shown by black color. Then you have an interposer, and I'll show you what that is. That makes connections through from the package underneath. And you can put here a GPU or CPU, your microprocessor chip that controls, for example, your computer. That is your heart of your computer. So that one will be here. Then you have some memory chips stacked. There is another logic die. And they build these things in the 3-dimensional fashion, because if you just lay them out on 2-dimension, the amount of space that is taken is quite a bit. So they are now expanding this in the vertical dimension. Here is a cross section of 2 types of packages. One is called 2.5D, which is, you know, what I said, it's 2-dimensional. You have 2 chips at the lower level, and then you build a top chip on the top of it, and you connect it through these copper pillars and solder bumps. And in between, metallurgy is conducted here using RDL process, which is redistribution layer. So you have to build some wiring. So some of the wiring that you do in the die is taken up by these redistribution layers as a separate material. So that reduces the process cost, and you're able to have a lot more flexibility in terms of how you design these packages. Here is a complete 3D package, which is called chip on wafer, COWOS, chip on wafer on silicon. So you have a circuit board onto which these are the package balls that make connection. You have a packaging substrate that is plastic or ceramic. It has all the wiring inside, and then you come through this silicon interposer, which is a wafer with holes made in it with copper connections. These are bigger holes than the nanometers we talked about, to just bring up the power from the bottom. And then you put a logic chip, you put another computing chip, you put a base die, it could be your microprocessor. And then on the top of this, you put this high bandwidth memory DRAM chips. There are 4 in this particular case. And they're all connected through a process called through silicon via. Via means a hole. So you drill a hole through this and you deposit copper, electroplate copper, like I said, and you make a conduction right from the circuit board all the way to the top of the chip. So this is a latest packaging, developed in last 3-4 years by TSMC. The same one, if you look at in the three-dimensional isometric view, it looks like this. These are the chips sitting on the top that I showed. And this is your silicon via TSV through the silicon interposer with a bunch of copper pillars. And this particular package can be installed into your computer. For DRAM, Samsung has come up with a 512 gigabyte DRAM 5 chips. What they basically do is they put 16 gigabyte DRAM chips, 8 in stack. So it's an 8-story building, if you will, connected through the TSVs all the way. So it makes a tower, and there are 4 such towers to make up to 512 gigabyte. So this is 16 times 8 times 4, that will give you 512. So need to explore the vertical dimension now, and that seems to be the way the fabrication is going in that dimension, because we are running out of area in the X and Y dimensions because we cannot print stuff any smaller than certain dimensions. Cost gets high, number one, and we may not have the machines that will go down below, say, 5 nanometers. Now, this is the evolution of the packaging. In 2016, if you had the normalized transistor count of 1, you were able to bring it to 20 in about 5 years, 2016 to 2021. And basically, this is the same package I described using interposers, new TSV process, high bandwidth memory chips with copper interconnects, etc. And it's going to go further. And nobody knows how it will look beyond 2023. But hopefully, continuation of the progress will make us move through this path. That's the hope. So this is the COWOS process that I just showed before, chip on wafer on silicon. Now, what are the challenges in the front end where you have to really make a good device? There is called channel engineering. The channel is the one in which silicon device resides. And there is a lot of science that goes with it, a lot of physics and a lot of math. Smaller geometries are required using advanced lithography tools I showed you. The gate oxide engineering. Gate oxide was silicon dioxide, and it's running out of steam beyond 10, 20 angstroms. And now you have to give high K material. K is the dielectric constant. Why do you use high K? Because transistor is like a capacitor. It has a dielectric constant, and it's like a dielectric material. So higher the dielectric constant, more power you can pump into it. And the gates are used of metal instead of polysilicon. And then moving into 3D device, which I'll show you how it is done. Contact metallurgy, platinum and titanium are the 2 primary candidates used so that you form silicides onto which metals will make connections. And in the back end, you have interconnects and metallization where smaller vias with higher aspect ratios they need the reactive ion etch and the ALD process that I described. Without the combination of these two, you cannot build any interconnects. Conformality is very important. All these layers you put have to be conformal, same thickness throughout the entire topography, and the line of resistance is coming into play, because as you reduce the line width, the liner material that is put under the copper takes up much of this thickness, and that thickness of that seed layer and the resistance is much higher. So there is a limit how much we can shrink these lines dimensionally. Chemical mechanical partial etching processes, there's a huge development needed. Low RC constant for performance. This is key, and I'll show you some of the charts, what we are doing to keep the RC constant low. RC constant is the one that will limit your access time. So all the high performance transistors you build, unless the RC constant is low in the back end, you cannot get all that performance translated into the actual function of your computer. Copper wiring is the latest state of the art. Liner metals are investigated in terms of lower conductivity for smaller lines. Global wiring capacitance, I'll talk about and show you how that is handled. And 3D wiring in logic and memory and packaging innovation. So this is the heart of the development that is going on. So why do we need this development is basically shown on this chart. There are two critical lines that are followed. One is the gate pitch. Gate is where the transistor is built, and this is half gate pitch. Pitch is if you have a line and if you have space, center to center distance is called the pitch. So half of the pitch is like a width of the line if line and space are equal. So in 2020, this is about 27 nanometers, and it's going to go down to about 20 nanometers in progression. Same thing for metal. It is starting with about 18 nanometers and is going down to about 8 nanometers. So that's the path in which you need to build these structures to continue the performance that we need for our computers, our mobile chips, and our chips that go into the server machines. Otherwise, we will not be able to offer the performance and the densities that are needed. Density is basically the thing that drives this pressure on reducing these dimensions. So this is called scaling. So device scaling, mathematically, you can calculate how the devices will work for these dimensions. And scaling works up to this point, 2028. But beyond that, scaling is leveling off, as you can see. You cannot get any more juice out of these lines to get functionality. So we have to have innovations in this area. And this is an area where it's going to be explored very soon to figure out which are the candidates that will continue the technology progression. Now, on lithography side, we have done a tremendous progress. This chart shows you 1980 to 2020, we had lithography sources about 365 nanometer source. We moved to 248, and we went to 193 nanometers. And we were able to print smaller and smaller geometries that are shown on this y-axis down to 100 or even below 100. And we could go up to about 20, 30 nanometers using a few additional bells and whistles, if you will. And the same lithography machine, for example, immersion. Immersion is in the lithography machine, you have a water lens. Water is flowing in the machine and the optics is built around it so that numerical aperture is increased because water gives you much higher numerical aperture than the air. And you can go down in terms of resolution. Here is the extreme UV that I showed you, which is 13.5 nanometers, and that's in 2020. And it has come down to 8 nanometers, as I showed before, hopefully 5 nanometers, but going beyond 5 nanometers is very difficult. So lithography is coming to a screeching halt, if you will, and we need different ways of building devices to get more performance. And that is the next part of my talk. So the knobs available for device performance, we talked about the gate oxide, 10 nanometer SiO2, that's the limit. The silicon wise in the channel, there is strained silicon and there is silicon germanium, epitaxy. These are new materials. They already are implemented. In the gate oxide, high K, aluminum oxide and zirconium oxide has replaced the oxide. Metal gates, we have removed polysilicon, we have gone to aluminum, and gate length, we are able to reduce it with lithography down to 8 nanometers. And how do we go now from 2D to 3D devices with multi-gates? And that's the next topic we'll do. So here is how we will be progressing. This is how we are building the stuff today. If you remember the device that I showed in the first initial slides, you have a planar silicon and you have the isolation oxide and you put a gate around. So this is an XY dimension, two-dimensional device, either built on bulk silicon or SOI. SOI is a silicon on insulator. So you have this silicon and there is a oxide on the top, and then you have this silicon layer on the top of it. And this is how the material starts. And this isolates the substrate, and you have better performance of the device, especially in the RF applications, where you need really noise-free transmission. Now, from these planar devices, we are moving to using FinFET. FinFET is basically, we got a fin of silicon sticking up and we put a gate around it. So the cross-sectional area between gate and the fin is increased more than the cross-sectional area we had before. So the amount of current that you can pump through this is much higher than what we were able to do with planar devices. So you get much higher currents. That means you can get more power coming out of these devices. This can be built on bulk as well as on SOI wafer. So that's the phase we are in. From here on, this is the next phase where we will be making gate all around. GAA is gate all around. So here is your silicon. Let's say this is your needle of silicon, which is a nanotube. Let's say, you might have heard the word nanotube. And onto nanotube, you coat this gate and you have an oxide in between, and that's your device. Now, how can you use it effectively? There are two ways. You can make lateral arrangement or you can make a vertical arrangement. Vertical arrangement is easy. You have the bulk silicon underneath and you stick up these needles in the vertical directions and form a gate around. And that's your vertical gate all around structure. If you don't think you can do it this way, there's easier ways using in a planar or lateral structure where you lay out the first device. This is your silicon line. Then you have another layer of silicon built on the top, and there is gate all around, and there is space in between the two. Now, these are all schematics. How you actually build this is a very difficult, but I will show you how in IBM we have made these structures down to 2 nanometer performance. So this is the path we are going right now in this area. This is older technologies. This is where we will be exploring from here on. This slide just shows you how intensive it is in terms of developing these technologies. It takes about 11 years for new technology generation to go from, say, strained silicon, then you went to high K material, raise source and drains, multi-gates. So these are the steps we are taking, and each of these take 11 years. So you have to pump in a lot of research and development money for 11 years, before which these options go into actual manufacturing. So this is a very, very capital intensive and time intensive business, just because it's very complicated. That's the only message here. Now, when all is done, what does it mean for a microprocessor? So this is an interesting chart. Over 40 years, microprocessor trends have been plotted. And Mr. Moore from Intel, he created a law called every 2 years, he said, transistor density will double. And this is that red line on which he said we will be making denser and denser devices. And he was right up to, say, 2015 or even up to 2020. But beyond that, this thinker is flattening out. So you're not able to get device densities that you need on this curve using two-dimensional structures. So we need to go to the 3D devices that I showed, which will make a continuation of this path. And again, you don't have any data points here to plot, but another 3-4 years, you will have more data in this line. And that green one is the frequency of the transistor in megahertz. This is about 1 gigahertz, and silicon is flattened out at about 1 gigahertz. We are not able to get any more performance out of silicon by all these things. Now, so how are you going to improve your performance of the computer? So now they are going to go to parallel process, where you use high number of logical cores. So in each core, there is a microprocessor. So you'll have, say, 20 cores, you'll have 20 microprocessors working in parallel operation. And you do the parallel operation so that in the end, you accomplish your goal, but you do not do it with brute force using one core, because it's very limited on performance, right? Its frequency is flattened out. They plot this single thread performance, spec integer, spec to see how you're performing your cores, and there is some path along which we will be making progress with the blue line. So there is some hope that we will get this curve beyond that. So this is very important chart, because this covers almost 45 years of trend, which has been going on, and mathematically people have been able to predict what will happen. Here is an example of 3D memory. I just wanted to show you. You build up these stacks, and you have these cores through which connections are made. This is a very complicated process, and each of these dimensions here, they look very big, but they are of the order of maybe 10, 20 nanometers, or maybe a little bit bigger than that. In terms of lithography, from 2013 down to 2021, we think we came down to almost 3. I showed about 8, but there is some hope that we can go there. Beyond this, there is no way we can build anything. And 3D is the way to go. So that's the basic chart here. These are some of the structures, 3D structures that are being built. The one I showed you, these are the needles that you, as I said, these are the needles, or these are the silicon shapes, pink ones, that are sitting on the top of each other, and they are connected by the sidelar structures. And here is a vertical gate all around. So you have one plate here, you have another plate, source and drain, and there is a channel in between. And around the channel, you have the gate all around. And this is what is today built in development. And it's going to go over here from 2030 to 2034. So there is a path of building devices beyond that, nobody's guess. This is another cartoon which shows the same concept, but a little bit more elaborately. This is how planar devices are built using two-dimensional structures. Then you build a fin, and then you build the FinFET around it. And then instead of one fin, you basically have three in the horizontal direction, and you have source and a drain, and then you have a gate all around. And this one in cross section looks like this. So here's your channel, here's your high K material, and then you have the gate all around. So basically three terminals. You have the gate, and you have source and drain coming out of these ends of the silicon material. Schematically, this looks very easy, but actually process-wise is extremely difficult because these channels had about 5 to 10 nanometers thin. And the question is, how do you make that with the uniformities that we need? So IBM has, so I'll skip this one. IBM has taken a stab at it and basically built a 2 nanometer technology, which is shown here in the sketch, actual SEM cross-section of the devices made. And this is built around this scheme that I showed before. You have three tiers, 1, 2, 3. There are three tiers of transistors, and you have gate all around connecting them to give you huge intersection area between the gate and the source drain to give you a huge drive current. And power can be reduced now because you have a lot more current available. So you can reduce the voltage, you can get lower and lower power, which is very beneficial. The same structure, when you take it out of the chip that is built here, this is the same old picture that I showed before. That's about 40 nanometers wide. And if you take a vertical TM cross section through this yellow line, this is how it looks. And basically you have a L effective of 12 nanometers, that is the gate length. You're about 44 nanometers from one end to another end. And these are the three ribs that you can see of transistors. And the thickness of the silicon is about 5 nanometers, very small. And 1, 2, and 3 in that fashion. Now, after building this, what do you get? You get 45% performance improvement and or 75% power reduction compared to 7 nanometer device. So this is huge improvement. So now with this, you can make a cell phone and you don't have to charge it for weeks. It will not lose power because its power consumption is reduced quite a bit. So that's one application. The question is how expensive this will be and can we afford that cell phone is another question, but technology is available. Okay, let's move on. This is reality where the fabs are fabricating 10 nanometer technology today. Samsung, TSMC, and Intel. And Intel is far ahead of everybody else in terms of transistor density. They're building 100 million transistors per millimeter square, whereas others are doing 50 to 60, using the same ground rules, but they are able to execute these ground rules with much tighter specs. You can see here the transistor gate pitch is 54, whereas others have 66, 64, 68. So Intel is aggressively pushing this. They are successful. Using this technology, they build their Cannon Lake microprocessor that is gone into servers. So this is where state of the art has been in a few years back. 2015 was the plan, but actually in 2018, this was built in manufacturing. Now, where do these chips go? The major market for silicon chips consumption is really in the server area. These servers are data centers. As data centers use huge amounts of servers. Server machine is a big computer which handles huge amount of data, but consumes huge amount of power also. So it's a heat source and it's bad for the global warming, but we don't have much choice. We have to run these computers to handle huge amount of information. And the percentage of share of data centers with servers has gone up. This is almost half of the data centers have servers. Without servers, you cannot really run data centers because amount of information coming at the data centers is so huge. And there are about 485 worldwide. There were 259 in 2015. So in 5 years, as you can see, there's a huge growth in terms of server demand, in terms of server percentages in the world. And it's been going up and up. So beyond 2020, I'm sure this will be a, exploding. That's where all your chips are going. Now, in the interconnect technology, I'll talk about in a few more slides. The challenges are we got to get tungsten in contact with silicated silicon, and these dimensions of tungsten contacts are reducing. So processes need to be developed so that you can make conformal fillings without holes. The via drilling in the reactive ion etch with higher aspect ratio continues to be always the challenge, even in the back end as in the front end, and atomic layer deposition process is used. So this one thinks like it will work. RC constant reduction is done by using low dielectric constant 2.3 versus 3.0. And this is with new materials that are coming in. And there is further path going below 2 down to 1. One is air. They actually build some circuits using air and shown that the dielectric constant is very close to 1 for the chip, and RC constant is brought down. But in reality, circuits built with air instead of any dielectric may not be a practical approach because they are not hermetically sealed. You may have corrosion and so on and so forth. Copper plating versus aluminum lines we talked about. Repeaters for global lines. I'll show you some charts where repeaters are needed to reduce capacitance on global lines. Liner materials, new materials are needed because liner resistance is becoming a significant portion of the line width as you shrink the lines. Ruthenium metal is being looked into to replace copper for 8 nanometer technology. Defect density reduction is always a challenge, and low-K dielectric in combination with some of these things we are talking about will lower the capacitance. 3D interconnection and metallization will continue, and advanced packaging also will be continuing. Now, if you look at this chart, this is the cross section. You have the transistor built at this lowest level, orange color, 2 transistors. And you have contacts using tungsten, contact over tungsten here, another contact. And this is the first metal, black one, which is thin. And then you build vias, and then you put another copper metal in these holes, and then second level of copper or globalization. That means you can have multiple 3, 4 lines like this, and the 4th level or 5th level of metal will be thick. That's called global interconnect, because it globally connects all these wires, and then currents are very high, so you need fatter wires and thicker wires so that the juice can come down to the transistor and you can turn it on. And the delay in arbitrary units, circuit delay, is coming from 2 sources. One is the transistor and one is the interconnects. And as you can see on this chart, interconnects has a huge contribution to the delay, and transistors are really flat. So whatever transistor performance you get by reducing the size and putting a lot of money in research, most of it gets wasted unless you handle the back end part, because you lose all that capacitance, all that delay is coming from your back end, and it's killing your transistors. So what they had done on this side, you can see the actual picoseconds delay used to be very high for, say, 130 nanometer technology. So they moved from aluminum lines and oxide as the dielectric and metal to copper and low-K. And you are able to bring it down from 25 picoseconds down to about 5 to 10. So there is a huge reduction obtained. And now we need to continue on this path with ruthenium metals. Another metal we need besides copper, and flatten this curve as much as possible to lower ground rules. These are some of the resistances and constants that are going with these materials. Aluminum and copper lines, they cut them down to about 43 micron long sections, not beyond that. So you don't run any copper line, which is 100 microns. You make it say 40 kind of thing to limit your capacitance. And then you build additional layers of wiring for connecting them instead of connecting at the same level using multiple transistors. So these are some of the tricks that are used in the end. But this is key. This is really the challenge that we have. Now, what we have done is that's the challenge I showed. Now, here is the actual data. Where gate delay, the blue line is coming from your transistors, that is well behaved. The pink one is the local connections. That also has been reduced in length. So this one is very well under control. The delay is not going up. But the problem is with the global wiring, because they are thick and they are fatter, so the capacitance is very high. And they need to make them thick and fat because you need low resistance for the global wirings. It's like the current is coming into your house through underground cable, which is very thick in metal, and the thickness of the wiring inside your house is much smaller. It's the same concept. So what they're able to do, and I'll show you how it is done. They are able to bring it down in the green line. So this is rather behaved properly. We need to still make more improvements on it, but there is a big improvement that is in the works. Now, how does this work? Is if you have a 1 millimeter long line, let's say, and it has 100 ohms of resistance, its intercapacitance between two lines is 0.01 picofarad, and the delay time is about 1 microsecond. If you make this line double the length, resistance goes up twice, capacitance goes up twice, and 2 times 2, 4. So RC constant becomes 4, so you get 4 times time delay. Now, if the 2 millimeter long global wire is cut into 2 1 millimeter pieces, what will happen? You will get 1 plus 1, which is 2 microseconds of total delay versus 4. So you cut it down by almost half. And that's the trick that is used when they are using global wiring with repeaters. And they are able to manage this. This is actual data. So this thing needs to be worked on more from a circuit design point of view, but these are some of the solutions instead of going into changing materials altogether. That's all I have. Thank you very much for your patience. I know it was a long presentation, but I appreciate your attendance, and I do thank you again.
Thank you, Subhashji. With your permission, we can move to Q&A. There are a few questions that we have received over the chat. So I'll read the first question that we have. What's the future of eFPGA and chiplets? Is it becoming or going to be trend for future development?
What's that material again? EF what?
eFPGA.
Or eFPGA. Yeah. FPGAs are field gate arrays. I think they are still available. There are advantages in building those because you can change the process and change the design very rapidly and make those available. So I think they will be still in market. Yeah.
Thank you, Subhashji. There is another question. Since these transistors are created at nanoscales, how do you make sure that circuits developed have the design as how it looks on paper? Do you see it through some kind of nano microscope, which is projected on a big and large screen to be sure that designs are correct?
Yeah, so there's a whole science behind it, and all these shapes that are fabricated, they are verified using top SEMs or SEM cross sections. Scanning electron microscopy is used all along. And scanning electron microscopy has enough resolution to give you feel for how they are, how thick they are, etc. They can be also looked at in three-dimensional areas to see if the corner rounding is done properly, so connections are made. And that keeps on going all the time in terms of construction analysis. And it goes at every level, so you can check at every level. Second thing they do is there is a design verification process where you build a program and you specify your ground rules. You say, I'm going to make line width this much nanometer. I'm going to make contact hole this much. Tell me what the resistances will be, and they will calculate all those for each circuit. And they will make sure that the assumption that is made in the circuit performance is conforming to those actual values, because that's very important. There is constantly data feedback process that is going on in the design verification process in terms of layout. And there are companies that do the design layouts that have a huge amount of money invested, a lot of engineers work there, and they will do that work for you also if you are in contract with them. So some of these fabs do take help from those companies.
Thank you, Subhashi. How is the next question is, how is CMP and WOC chip affect each other in future? Is wafer on chip and SoC system the same?
Repeat that, could you please again?
How is CMP and WOC chip affect each other in future? Is wafer on chip and SoC system are the same?
There is a overlap between the two. SoC is a special application, system on chip is a special application of that particular chip, how you use it. And if you want to make in general, a three-dimensional package for any application, you can make it. So that's really, so one overlaps the other. And in the Venn diagram, if you will, there is significant overlap, if I may say so.
Okay. Thank you, Subhashi. The next question is why we have not moved to gold from copper?
Gold looks very attractive from the resistivity value, but it's very expensive, number one. And the chip cost will just shoot through the roof. So I am not sure whether that's really a worthwhile option to pursue. Again, even to evaluate this in development, because you have to do a lot of reliability studies of these circuits. You have to make sure electromigration wise is good. That's very, very expensive, even for a development organization. And now the big question is, after having demonstrated that it is super duper, will anybody in the fab go and invest money in the gold? That's something I am a little doubtful about, but hope we don't have to go that way. There are other candidates between gold and copper that are being explored, like ruthenium, I said. So let's go through that first and figure out where we go. Okay.
Thank you, Shivaji. Just a couple of more questions.
Sure.
How much is India dependent upon the other countries for the mineral resources for semiconductor manufacturing?
Okay, India is way, way behind in manufacturing. In fact, I was invited some 10, 15 years back as a consultant by Government of India to address the situation of manufacturing. Now, again, that is old, things have changed. So I don't want to say that is still existing. But my assessment was we don't have the infrastructure, because to build a fab, first of all, you need huge amount of money. You need huge amount of water, because these wafers are washed after every one step that is performed. And you have thousands of steps. amount of water consumption is very huge. And country like India, where water shortage exists, if you build a fab in India, say for example, say Pune, okay, you will be robbing the water out of millions of homes. And that just will not fly. That's my first reservation. Once the water source is available somewhere, huge amount of water, then it could be looked into. But then the next hurdle is infrastructure. These are poisonous gases that are used. You need roads that will not cause accidents. If you have a poisonous gas spilled on highway, that will kill huge number of people. It will be like Bhopal, for example, okay? And there will be many, many accidents like that because our road conditions are not good. So those things have to be improved. Now, China made a lot of progress along those directions, and they laid the infrastructure first. In India, is the other way around. Let the investors come in, and then we will provide roads for them. That's the way the Indian strategy is. So I am very skeptical. Now, low-end parts can be made in India that are really dirt cheap, but there's a huge competition on that. There are so many other countries like Singapore that can very easily break prices, and we will not be able to compete. So that's my gut feeling.
Thank you, Subhash. So, like the follow-up question on this is, what is the future for semiconductor manufacturing in India?
Okay, there are people who are investigating this. There are talks, and they will be building smaller fabs for specific purpose. For example, defense. Okay, if you need specific chips for defense, which are not silicon chips, but they are, say, gallium arsenide, because some of these exotic materials are used in the chip industry for specific purpose, because they are used in the optical world. So if you need to build some goggles that will be used by soldiers, by night goggles, then you need some devices put on their goggles. Those things could be made in India, because defense budget is kind of open-ended. They don't have restrictions. So some of the special items can be built in India. I think that's possible.
Okay, so we are almost on time. So the last question is, can we ever run out of silicon? If yes, what is the substitute?
Yeah. Okay. We will never run out of silicon, because silicon comes from sand. SiO2 is the basic material. There is a ton of sand all over the world. And silicon crystals are grown by extracting sand, SiO2, turning into silicon. And that's one. There is tremendous chemical vapor deposition process available to deposit silicon, polysilicon ingots. Lots of chemicals are available. I don't think we'll ever run out of silicon. And if we do, the other materials are more scarce. So I think that we just have to live with silicon. Silicon might run out of steam in terms of performance, like you saw in the charts, but they are going around it with intelligent ways of building servers with multiple cores and so on and so forth. So I think there is still some room to grow using silicon before we dump it and say, hey, I need new material. You know what I mean?
Okay. Thank you, Subhash. I think there is a live question coming from Manojji. Manojji, please go ahead with your question.
Yeah. Hi, Dr. Kulkarni. Excellent
Hi.
presentation. My question, when you answered, was system on chip and wafer on chip. So I was speaking to somebody who does research on organs. So, for example, they call organ on a chip. So they want to do some research on a lung or on a blood vessel or on the heart. And instead of going through the clinical trials, they're trying to model that organ on a chip. So they call it system on a chip or organ on a chip. So in the initial discussion, you mentioned that system on a chip and wafer on a chip, they have some intersection. So is it like you can take multiple, I guess, wafers or multiple chips and then form a system on a chip? Like, how does it, is there an example you can kind of give, or can you just elaborate further if you don't mind?
Okay,
Thanks.
system on a chip is a concept where just forget devices. What do you have? You have a processor that actually processes your logic. You have to have
Right.
logic commands built in, and your microprocessor will do that. But it needs RAM capacity to store data, and the RAM
Right.
capacity will come either from DRAM or SRAM, and you have
Mhm.
to have a large amount of cache available on chip, because
Mhm.
that is the prime chip memory that can be fetched into the microprocessor very fast.
Mhm.
And if you try to bring it from a DRAM, first of all, DRAMs are slow. It takes long time to actually process it, and so on and so forth. So cache memory on chip is prime memory, and depending on your application, what you're trying to do, you need to decide how much of that is needed. Because once you know that, that detects your size of the die that you're going to make. If the die size gets too big for manufacturing, because manufacturing has defects, and the defect densities will affect larger dies more so than smaller dies. So if you say, hey, I need a 25, I need a 1 inch by 1 inch die because I need to put so many functions on my chip, the foundry will say, boss, it's going to be huge expense. So first, that's what you'll have to decide in your application, what size chip you need. And once you have a handle on that, then you need to know how much of internal cache I need, how much of DRAM, how much of SRAM I can have, and how many cores of microprocessor I would need. So all that has to be put together for an application before you start actual designing chip. Now, once you get to that point and know what the size is, and if the size is huge, then you go for, then you say, I cannot do system on chip. System on chip means everything is available on that chip.
Yeah.
Okay, that is system on chip. But if your die size goes really big, then you say, oh, wait, time out. I got to build these different dies, and then I got to go and build them on a package. The one that COWS I told you, that type. It doesn't have to be exactly that, but something like that. And you are going to lose some performance because you're going to be connecting through these dies instead of on die connections. So there are trade-offs, and if you can live with that trade-off, then you go and build a on wafer. So what I meant was overlap to the extent where both of these could be done using a system on chip up to a point. But beyond that point, you really have to go with multiple dies and advanced packaging.
Thank you. That was very well answered.
I hope I answered the question.
Yeah, it was very well answered. I used to work with Integris in Boston. We used to work with TSMC and Samsung, so I have some idea on those things.
Yeah. These are very aggressive people. They're capturing the business. Yeah.
Thank you, Manojji. Thank you, Subhashji. There is last question, which kind of relates to the use of quantum computer applications in several areas.
Yeah.
In your opinion, is the transistor technology changing?
When we go to computing.
So in view of like those applications getting applied to different areas, like how does it affect the transistor technology?
I don't think transistor technology will be affected. It's basically computing. Quantum computing is a way of application, if you will, in terms of doing things better than what you were doing before. So I think basic transistor technology will not change.
Thank you, Subhashji.
Yeah. Okay.
So that ends our Q&A. Like we'll move to vote of thanks. So on behalf of IITAC Board of Directors, organizing team, IITAC members, and special guests in audience today, let me call all it together fraternity of technologies at heart here together. I would extend a very hearty vote of thanks to our speaker, Dr. Subhash Kulkarni ji, for sharing with us his findings and opinions today on semiconductor technology. We all are certainly enlightened and inspired by your great words. Thank you very much, Subhash ji, for taking out your time and spending your Saturday morning with us.
My pleasure. Thank you very much. I appreciate that.
With that, I request all the attendees, so if they can switch on their camera for a while, we can have a nice group photograph. Okay, anyone else wants to go? Like, I'll give a couple of more seconds before I take a photograph. Okay, 1, 2, 3, say cheese. Thank you all. Have a good weekend, and thank you for joining IITAC on this Tech Talk.
Thank you.
Right.